Hello and welcome to Crystallite Academy e-learning platform, a one-of-a-kind virtual platform that offers you the opportunity to learn and grow at the comfort of your homes on your portable devices.
All right, at this point, let's quickly proceed to derive projectile equations or formulae for maximum height as well as range. We've done that for time taken for a projectile to reach its maximum height h, and then we've also done that for the total time of flight of the given projectile. All that's left is for us to derive the mathematical equation for the maximum height and then the range. So let's quickly get into that. I believe it's important that we split the board into two because there will be a lot of math going on here. All right, this is the third projectile formula, right? So maximum height. Maybe I should just draw a rough, tiny sketch of the projectile diagram. Now, don't forget that this is where our H is and this is our range. Good. So we have the projectile here, we have the projectile here, and it moves according to this trajectory. Of course, we are just managing our space, so you bear with me. All right then, now maximum height. I believe it is very smart for you to start by actually defining maximum height. From the image you can see here, you can define maximum height as the highest vertical distance from the Earth's surface, and it will do justice to everything. This is simply the highest vertical distance from the Earth's surface. Now, when I say the highest vertical distance from the Earth's surface, we are making reference to the projectile object itself, right? So the highest vertical distance reached by the projectile under the influence of the Earth's gravitational force. I believe you can look at it in that light as well. Now, next up is we want to derive a mathematical formula for this proper. So we can do that from the third equation of motion, which is v squared is equals to u squared plus 2as. Now let's quickly redefine these terms as we derive. Don't forget that at the maximum height h here, our velocity v is momentarily zero. All right, it's another point you want to note when you are defining maximum height. At the maximum height, which I said is the highest vertical distance the projectile gets to from the Earth's surface under the influence of the Earth's gravitational force, the velocity v also at the maximum height is momentarily, just for a moment, it stalls and its velocity becomes zero. So defining that, our v here, velocity, will be equal to 0, and our u squared, don't forget from previous teachings that our projectile is actually inclined at an angle theta, so our u squared will be equal to, u, let's begin with u first. U is u sine theta, right? We are moving according to the y dimension, and in the previous video I already explained why we are going with sine theta when we are referencing the y dimension. So u is actually equals to u sine theta, but we have the square of u, so that will actually be equals to the square of u sine theta. So we have u sine theta what? Squared. And when we do the math here, it will actually give us u square sine square theta. All right, that does justice to that. The next thing is our a is equals to our force of gravity, right? And that's negative g, once again in opposition to the effect of the force of gravity. Gravity brings objects down to the Earth, but the projectile is moving upwards, so gravity becomes negative in that instance. And our s in this case is not s but what? H, which stands for maximum height. Now let's quickly reference the original equation. From v squared is equals to u squared plus 2as. We now have something like this. V squared, v is 0, so it becomes 0 square is equals to, now u square is u square sine square theta, right? So we have u square sine square theta plus 2. Our a becomes negative g, so we have bracket negative g, and then our s becomes what? h. All right, let's proceed. Since our v is 0 squared, we know 0 squared is 0, so let's ignore everything on this side and bring our u squared sine squared theta to the left hand side of the equation. When we do that, of course, you should know from your knowledge of math that u squared sine squared theta will acquire a negative sign, because looking at this now, it has a positive sign even though it's not written. So we'll now have minus u squared sine squared theta, and then it will be equals to, we can decide to rearrange the signs here. Since we have 2 minus gh, we can bring the minus sign before this and say minus 2gh, and we'll still be right. So we'll be having plus minus 2gh. Simplifying this further, we have minus u square sine square theta is equals to plus times minus is minus, so we have minus 2gh. Don't lose focus, okay? And it's important that we capitalize the h because we are looking for the maximum height. We want an equation or a formula for maximum height, and 2g is stuck to maximum height, so we want to divide both sides by 2g. But before then, so at this point, what we simply do is, we have negative signs on both sides of the equation, so the negative would cancel out the negative, and what we'll be having left is u square sine square theta is equals to 2gh. Now we are getting closer to accomplishing our mission, which is to get a formula for maximum height h. The next step is we'll have to divide through by 2g. Divide through by 2g. Once a formula for maximum height h, but 2g is attached to h. The best way we can change the subject formula and make h the subject is to divide both sides by 2g. Doing that, we'll be having u squared sine square theta over 2g is equals to 2gh over 2g. Now 2g will cancel 2g, and we have our formula on our hands. Let's divide this into 2. Our h now becomes equals to what? U square sine square theta over what? 2g. This is the formula for maximum height. Very quickly, let's step to the other side of the board as we derive for range. Still making reference to this direction, making reference to this diagram, you can see that our range is the horizontal distance, the total horizontal distance. A graph has 2 dimensions, the vertical dimension and then the horizontal dimension. In our previous derivations for time taken for a projectile to reach its maximum height, don't forget that we're assigning uy to the vertical dimension and then ux to the horizontal dimension. So to define range now, we can just say this is the total horizontal distance. This simply refers to the total horizontal distance traveled by a projectile. To save space, I'll stop there. You can further add that, or you can put it this way. You say this is the total horizontal distance traveled by the projectile from the point of projection to when it returns to the Earth's surface under the influence of the Earth's gravitational force. Now, how do we derive an equation for this? I think we need to split the board here into 2 because there's a lot that will happen here. The equation of motion we'll be using for this will actually be the second equation of motion, and that's S is equals to ut plus half at squared. Let's quickly define these terms as we progress. Now we are looking for range rather. So our S will be equals to R, which is range, and our ut. Let's take a cue from this diagram once again. You can see that this is ui, but the range is in the horizontal dimension. So ut will actually be equals to uxt. So ut will be equals to ux. And also pay attention to the fact that range actually covers the entire flight time of the projectile from this point until the projectile returns back to the Earth's surface. So instead of small t, which is time taken for projectile to reach its maximum height, it will be capital T, which is total time of flight. So UT will be equals to what? UX capital T. But then we have already derived an expression for total time of flight, and it gave us the value 2u sine theta over what? G. Very good. So don't forget also that our A will be equals to G. And in this case, dealing with range now, as you can see, the projectile has actually landed back on the Earth's surface. So there's no effect of gravitational force in this instance. So G will actually be equals to what? 0. Now let's make reference to the first equation once again. From S is equals to ut plus half at squared. We'll now be having S is now R, right? So we have R equals to ut is now uxt, right? So we have uxt plus half. Our A is now G, so we write it like that. So A becomes G, and then our small t is now capital T, the square of capital T, which is total time of flight. Let's substitute. Our range R now becomes equals to ux is actually, from the first part of this video, I explained that ux is based on the x dimension of a graph, and from trigonometric ratio, we were able to derive and agree that when you are dealing with ux, you use u cos theta. Okay, you can rewind a bit to refresh your knowledge on that. So ux will actually be u cos theta, and our t, total time of flight, is 2u sine theta over g. So t is what? Let's say times 2u sine theta all over g plus half. G is 0, right? Times 0 times, we don't have space, so let's just put t squared. And of course, at this point, you know that when 0 multiplies anything, it cancels everything out and it becomes 0, right? Very straightforward. Let's simplify this further. Our range R now becomes equals to, our 2 multiplies everything over here, and our u multiplies u, and then we'll be having 2u squared. U times u is the square of u, right? So we have 2u squared cos theta sine theta all over g, and over here we have 0 left, so we just leave that one out. Now at this point, we'll be referencing trigonometry again in math. That's why I would like to re-emphasize again that if you want to be an excelling science student, you don't joke around with any subject. You must be serious with math, serious with chemistry, serious with biology, and even serious with English language. They are all interrelated in one way or the other. Now, there is a trigonometric identity rule called the double angle identity, and it is summarized as follows. Let me just write that out quickly. From double angle identity, identity, when you have 2 cos theta sine theta, it is actually equals to sine 2 theta. The double angle identity says 2 cos theta sine theta is equals to sine 2 theta. You can reference this identity rule and apply it at this point of the equation. When we apply that, we'll be having range R is equals to, if you look very carefully, we have 2 cos theta sine theta. So if we ignore the square of u, which is initial velocity, we can replace 2 cos theta sine theta with sine 2 theta. When we do that, we'll be having range R is equals to u squared sine 2 theta over g, and you're done. This is the formula or the equation for range in projectile motion. Very easy, very straightforward, nothing difficult about it. All you need to do is you practice this derivation a number of times so you can perfect it. Most students, funny enough, they don't really know how to derive this. All they know is they just memorize, and then when they get to their exam, maybe your UTME or WAEC or even your school exams, you mix the formulae up, or you just mess or jumble things up. This is how to go about it. As long as you can derive it, there's no chance that you forget this formulae. All right, so we bring our video on projectile motion to a close for now.